So this is the second lecture in the series of 4 that are based on material that I prepared for my visit to Tsinghua this fall in October and November. So the first lecture was on calibrated probabilities, right? So the idea that when a supervised learning system makes a prediction and it says, well, my confidence is 0.85, it should be the case that on new data drawn from that same distribution, 85% of the time it should be correct. So it's a strong frequentist notion of calibration. But maybe calibration is more than we need, right? Because in some sense, if we have a desired accuracy level, like maybe we want the classifier to be right 90% of the time, then maybe it would be sufficient just to have the classifier give us have what's called a reject option, right? So the classifier either given a new query, it looks at it and says, oh, I'm not going to be accurate on this one, so I'll just reject it. And otherwise, I'll go ahead and classify it. And the guarantee is of the ones that it classifies, it's correct 90% of the time, or whatever our target number is. So that's the idea of learning with rejection. So we're given training data. Let's say we'll assume we're in the standard supervised learning setting. So the x's are feature vectors, the y's are class labels, but we have a target accuracy level of 1 minus epsilon. And we want to learn a classifier f and also a rejection rule r. And at runtime, given the query, we'll first ask the rejection rule, the convention has been with rejection rules, if it outputs a negative value, then we reject. So if the R does not fit, then you must know. And if the rejection function is less than 0, then we reject. Otherwise, we use the classifier, the answer from the classifier. So you can sort of think that there are sort of 2 main strategies that are followed here. One is that you go ahead and learn your function, your classifier in the usual way, and then after you're finished learning, instead of calibrating the probabilities of the classifier, you develop some sort of a rejection rule based on the classifier and using some validation set data or calibration set data to do that. So then F is the primary thing and R is just learned afterwards. The other thing that's been tried is to learn F and R together. Because when you're learning F, if you know you're going to give up on a certain set of data points, then you can do really badly on them. You just do not care how bad you are. Whereas, usually the function is trying to do well on everything and may even make a trade-off doing a little less well on some things in order to do a little better on some others, right? So maybe there's an opportunity to do well on more data points if you know you're going to reject some. Now, of course, if you just reject everything, then you get the trivial solution. So in general, there's a trade-off here. Obviously, you would like to reject as few queries as possible and yet still achieve this 1 minus epsilon accuracy. So those are kind of the rules of the game here. And so this lecture, in each of these things I had a reading assignment. So these were the papers that I assigned them to read. I particularly recommend this one. It's from 2016, so it's relatively recent, but it's in the kernel machine, support vector machine space, and I'll cover that in this talk. And then I'll talk a bit about this other framework that's known as conformal prediction. Although for purposes of rejection, as you'll see from my experiments, I don't think it's really the right thing to do. Okay, so the basic theory. So it turns out, you may know the Chow-Liu method for learning a undirected graphical model. Well, Chow is a busy person. And he also published a paper on the theory of rejection. So under the assumption that we can learn the perfect classifier, perfect probabilistic classifier, then he proved that the best prediction to make, of course, is the one that maximizes the predicted probability, the class that maximizes the probability. And the optimal rejection rule is just to reject if the predicted probability is less than 1 minus epsilon. So this is a very clean case. And probably, you know, from our vantage point, however many years later, we could do this as a kind of homework assignment. But so that's the basic case. But of course, in general, we're not going to have that optimal function. Well, if we don't have that optimal function, we can still determine some threshold that gives us a performance guarantee. So just as we did last time when we're trying to calibrate our classifier, we can build a data set, a sort of a new data set that consists of the predicted probability that, so let's let y hat I be the predicted class with the highest probability or highest confidence. So we put our confidence value for that, and then an indicator, 0, 1, of whether we're right or wrong. So this is our calibration data set, right? And last time we then tried to fit a function to that data set so that we could turn these approximate probabilities or margins or confidences into actual probabilities. But in this case, we just sort them by their increasing value. I'll call them the p hat values. And then we just choose the smallest threshold, tau, such that if f of x and y hat is greater than tau, then the fraction of correct predictions is 1 minus epsilon. So we can think of our sorted values as giving us a cumulative distribution function, right? Or at least a cumulative distribution of the probabilities. And we want, if this is the 1 minus epsilon line, then this is the threshold we want. And we can turn this into a formal statement. And so I looked up at the stuff that Siliu had done for our paper on out of category, which if I get around to lecture 4, we'll discuss that work. But there is you can get a finite sample guarantee, a PAC guarantee, using this bound from Massart that relates the distance between two cumulative distribution functions, that is between a true CDF and an approximate or empirical CDF. So it's a lot like other central limit theorem things, or like the Hoeffding bound or the Chernoff bound, but this is a bound for CDFs. And what you end up with is if this is your empirical CDF that you fit to the data, the black line, you get basically error bars around it, and you can set a threshold on the upper error bar so that you guarantee to have the desired coverage. So you get something reasonable in terms of the sample size. You don't get a guarantee of 1 minus epsilon, you get a guarantee of 1 minus epsilon plus another error term eta. And the sample size that you need is quadratic and 1 over eta squared. So it only takes a polynomial amount of calibration data to get a decent bound. Okay, well, there's another paper that tries to do the same thing, but instead of using that kind of uniform convergence bound, they do a kind of confidence, a binary search, right? Because we're searching for this threshold. And so you can sort of think, instead of trying to get uniform bounds around the CDF over the entire range, we could just probe here and ask, well, where is it? Oh, it's too high. We go down here, oh, it's too low. And we could zero in to get the right threshold. And if we can do that in a relatively small number of queries, each time we make a query to the data, we use up some, we need some statistical force. And so they use an exact binomial confidence bound for each of those probes. And then take the union bound, also known as the Bonferroni correction, over all of those separate estimates, because you have to estimate the CDF at each place you probed. And they also get a polynomial time bound, although I think actually this one is tighter. But it would depend on actual experience. This one is sensitive to the actual data distribution. Another thing you can do is, if you have already calibrated your classifier, then you can calculate what the rejection threshold should be if you set up the following thing. So we can think, if we have the probability that y belongs to class 1 and the probability that y belongs to class 2, and if we and then we have 3 actions available to us, right? We can either predict class 1, predict class 2, or reject. And presumably, if we predict class 1 when the true class was 1, then we have no loss at all, and we have no loss if we predict class 2 correctly. But these are our errors, right? So this is when we predicted 1 when the right answer was 2, or predicted 2 when the right answer was 1, predicted 1 when the right answer was 2, and if we rejected here. So these would be, this is a cost matrix for our classification problem. In 0, 1 loss, we would make these both 1s, but in general, they could be arbitrary, although probably the maximum should be 1, you know, we can rescale. And these costs should be somewhere between 0 and 1, right? Because if it costs you 0 to reject, you just reject everything. If it costs you more than 1 to reject, you're always better off trying to predict. But you could set your rejection cost here. And so you can set this up, and if you have calibrated probabilities, then you can just calculate for a given choice. These will be estimates, but they'll be calibrated, so you can choose, you can calculate the expected cost of predicting 1, of predicting 2, or rejecting, and just do whichever one has the minimum cost. So that's another advantage of having calibrated probabilities. But if you don't have, but another thing you could do is try to set up, if you didn't have calibrated probabilities, you could try to set up an optimal classifier. But now, because you have different costs for the two kinds of errors, you actually have a little bit more complicated rule here, right? You have to ask, how confident am I about class 1? And if I'm confident enough, predict that. How confident am I about class 2? And then there's a different threshold, and predict 2, and else reject. And so you end up now having to search not for one threshold, but 2 different thresholds. And in a K-class problem, you have a lot of thresholds. And so there's a paper by these guys, Dietterich, where they have a fast algorithm that's based on they're using isotonic regression. So in a sense, they are calibrating. But they have a clever way of computing the slopes of the ROC curve to make this search very fast. So it scales well. Okay, well, what else? Now let's suppose that we leave the land of probabilities and we move to support vector machines. I don't know how many of you have studied support vector machines. It used to be we would spend tons of time in our classes, but now we spend more time on deep networks. But I'll give you a little review here. So of course the key idea of support vector machines is we're going to maximize the margin around the decision boundary, and I'll explain that in a moment. And so people have studied 3 different things. One thing to do is just fit the standard support vector machine and then either calibrate it or threshold it to get your rejection rule. But the other 2 attempt to simultaneously learn the classifier and the rejection function. Okay, and so to do that, they set up a loss function of some kind that looks at both of those decisions together. And the first paper was something called the double hinge loss, or DHL, that came from Peter Bartlett and one of his students. But then more recently, Corinna Cortez and her husband and one of their collaborators have learned 2 separate functions, but they also have an even more complicated loss function, but an easier computational problem to solve. And experimentally, their method works better. So a reminder about the standard support vector machine. So our decision boundaries will be linear, although we may kernelize them, but we'll ignore the kernel issue today. And so the idea is we want to find and we code the class labels as +1 and -1. And then the function, the classifier or discriminant function, f, that we learn, will also give numbers on the real line. And so, and be classifying as positive if f of xi is positive, and as negative if f of xi is negative. So this has the nice property that the correct prediction is found if yi times f is positive, right? You see they're both negative or they're both positive, then xi is correctly classified. So geometrically, right, we want to find, we have a bunch of points labeled as minuses, a bunch of points labeled as pluses. There are many different linear separators, let's say, in the linearly separable case. And so the idea is to define this notion of a margin on each side of the separating hyperplane, and to try to find the hyperplane that maximizes that margin. And in this case, that would be this one, and not the green one, right? Because the green one has a much smaller margin of wiggle room around the separating hyperplane. And this can be achieved by solving a convex optimization problem. And of course, that was one of the cool things that support vector machines brought into the machine learning conversation, was to say, first of all, you know, we want to minimize 0-1 loss, but we really can't do that. That's a very nasty loss function. It's discontinuous, it's not differentiable, it's a mess. But if we approximate it with the so-called hinge loss, then we can get a convex optimization problem. And so we get the wonders of convex optimization. So the formulation here basically says we want to minimize the norm of our weight vector. So our function, our classifier is this thing, w dot x plus b. So a weight vector times the feature vector dotted with the feature vector and then some intercept term. And we minimize the size of the weights. So this is like weight decay in neural nets, plus a term that is about the hinge losses, which are these slack variables in this formulation, right? So if y times f is positive, then eta can be 0, or xi, I guess. Xi can be 0, and because this is greater than or equal to 1. And if this is less than or equal to 1, then we have to add some extra fudge factor, and that goes up here in our objective, something we're trying to minimize. So the xi are the slack variables, and they measure how wrong we are at classifying each point. And c is our regularizer. The bigger we make it, the simpler the function needs to be. Okay, well, the idea of the double hinge loss came from this pair of papers. First Herbe and Wegekamp, and then Bartlett and Wegekamp. And the idea is to first think about, we're going to have a decision rule that looks like this. If y times f is less than some constant negative delta, then we're going to say that we're going to suffer a loss of 1. We're going to just get it wrong. And if y times f is in this range here, we're going to abstain, and we're going to have an abstention cost c, which is somewhere between 0 and 1. And if y times f is greater than plus delta, then we're going to be correct and suffer no loss at all. So you can sort of visualize that as this red curve here, right? If our y times f is less than this, then we pay this penalty. If it's greater than this, we're in good shape. So the original hinge loss would have had these two both be at 0, right? So we're pulling them apart to have an abstention zone in between where we're going to abstain. Now, of course, just like the 0-1 loss, this thing has a derivative of 0 everywhere except where it's discontinuous. So it's still a terrible thing to do. So what we want to do is get a convex upper bound on it. And so this is what they use, is this blue curve here. And then that's going to give us, again, a convex optimization problem. It turns out it's not a very easy convex optimization problem. When you write it all down, you end up with this thing. So this is, you know, we want to have, we have a set of two sets of slack variables, one for whether we're getting it completely right and one if we're getting it into the abstention zone. And our regularization shows up here in the dual. I tried to write it all down in the primal because I always find that more interpretable, but can't quite do that. Now this thing is a quadratically constrained quadratic program, right? So the standard SVM problem is a quadratic program, which is to say the only quadratic is in the objective function and not in the constraints. But this one has quadratics in the constraints too. I guess from that last constraint. So it doesn't look like it to me, but anyway, it's convex, but it turns out to be quite slow to solve. Anyway, so that's going to motivate this third method. But before we look at the third method, we might think a little bit about the situation. So if we're in this case, we're still trying to define our rejection function in terms of this function w dot x plus b that we're learning, right? So that's our assumption, is that we can find some way of thresholding that. In this case, we have two thresholds, or it's really this threshold delta. But that assumes that the rejection function f is monotonically related to the true probability that we would like to have. But it is possible for that to not occur, and particularly with linear separators it can happen. So this is a picture from one of the papers, I can't remember which one now, where these are our positive examples and these are our negative examples. And so if you're using a linear separator, you either have to put it down here somewhere or you have to put it up here somewhere, right? Because you really need two linear separators, right? But you can't get that with a single linear separator. And when so let's say red is the best decision boundary you can find, then it turns out when you build your calibration curve, it has this non-monotonic shape to it. And you can actually learn two different calibration thresholds against it and turn it into a calibrated curve, and that actually gives you these two decision boundaries. So it's just an example of where the value produced by the function f is non-monotonically related to the true probability you would like to be outputting. So, so this is one place where this strategy breaks down, is when that's true. Because there's no way to, I mean, if you took this and then calibrated it, you'd be okay. But our goal is to learn a separate rejection function. So that's what Cortez, DeSalvo, and Mori do. So they say, let's assume we have a two-dimensional loss function, right? So this is y dot f, and if I've probably got this, I guess if y dot f, this would be the positive direction. If r is negative, then we're going to abstain and we'll suffer the abstention loss c. And if y dot f is positive, then we are correct, so we have a loss of 0. And if y dot f is negative, we have a loss of 1. So we now have a two-dimensional loss space, right? So for a given point, if it falls in this quadrant here, then if we can reduce r, we can get it down into here and have a loss of c. If we could increase f, we could get it over here and have it be positive. So we can move in two dimensions at once. So this loss is quite a mess when you write it down. Well, and this is a convex bound on it. So this is what it looks like if you try to plot it, right? We have this area where y dot h, they're calling it h in this particular case, is big enough and you have 0 loss. But when h is small, you have a loss of 1. But if you could instead go over here in your r space and make r negative, then you'd step down to this loss here. So you have these three different regions, right, planar regions in the space. And so you can imagine trying to build some, hyperplane, upper bounded planes that are larger than it. In the paper, they actually have two different ones. So it's flat down here at some point, quite a ways past 0, and then it increases quite rapidly, especially in this direction. But now it's a convex surface, and so we can hope to optimize it. And so we're going to learn two different functions. F of x will be w dot x plus b, and r of x will be u dot x plus b prime. And you can write down the optimization basically to say we've got a regularization parameter for w, a regularizer for u, and then we're going to sum these xi sub i's. And the xi sub I is the slack variable appears 3 times. First, it has to be non-negative. That's boring. This is if we're screwing up with the r function. And this is if we're screwing up with both r and y. So by minimizing c, we're minimizing the biggest mistake we make out of these 3, which we can kind of view as basically there are these 2 planes, and we want to take the max of them to get this surface here. And so what we've written down here is this is one of those planes. This is on the rejection direction, and this is the other one. And then we want to take the max of both of them and make sure it's good. Okay, so they ran experiments on a bunch of Irvine data sets, and what they found, DHL is the double hinge loss, and CHR is their initials, so their method. I made this plot from the tables that they gave, and so you can see that the confidence intervals are somewhat wide, but in several cases they're doing quite a bit better in terms of total loss than the double hinge loss method. And here's the error rate on the points that they are not rejecting. So this is another way of looking at the results, right? This sort of says, well, wherever each of these methods decided to set its threshold, what was its total loss, right? That sort of cost-sensitive view. But the other view is to view it as a rejection function and just say, well, how many mistakes did you make? But you have to set them so that they reject the same number of points, right? And now we have the misclassification loss for having rejected the same number of points. And now you can see that their method is doing quite a lot better than DHL. Quite a lot better. Okay, so the conclusion I would say of reject options is that basic thresholding is really easy and gives you pat guarantees, so you could certainly do that in any application. Two-class thresholding, when you have differential costs, it's a little more complicated, but again, you can do it with a grid search, or you can be smart like the paper that I'm mentioning. K-class thresholding, I think I didn't see a paper that really looked at that. It's not even known whether having K thresholds, tau 1 through tau K, if that's even the optimal rejection rule in that setting. So there are mysteries there in such an elementary question, you'd think. Thresholding of support vector machines is interesting because we can think about trying to have a big margin not only at our decision boundary, but also at the point where we're going to be making the rejection decision, right? We want both of those decisions to be robust, and that's what the max margin framework kind of gives you. I guess I didn't emphasize that very much, right? But the idea of the double hinge loss, or of this one here, right, is that essentially we give ourselves a margin around both of these decisions, both the rejection decision and the classification decision. So that feels like an important idea. But a big open question, and I sent it to Fuxin this morning for the DeepNet class, would be, how would you jointly train a DNN and a rejection function? So somehow you'd want to have a deep network that, say it's just a classifier, but it's going to output K values using a softmax or whatever in the usual way, but then it should also have a rejection signal, and you want to be sure that when you reject, when you don't reject, that you're accurate, according to some desired threshold. So the input to the algorithm has got to be, I guess, a training set, a calibration set, and this desired accuracy level. And so you train on the training set and use the calibration set to decide on your accuracy level, to whether you're meeting the accuracy level. But somehow you would like to take advantage of the idea that, oh, I'm rejecting these guys, therefore I can stop backpropagating them through the softmax because I'm not going to use the softmax. And I think there's another opportunity here, really. I mean, very often you might want to use additional features that would go into the rejection decision that are distinct from the sort of content things. Like, I don't know, if you could read the EXIF data from the original camera, you might say, oh, this was shot on a lousy camera, so therefore I'm going to reject it. It's just, or you might be able to tell there's a lot of noise in the image. Maybe there was fog, dust, pollution, droplets on the glass, all the kinds of things that, like Dan Hendricks is trying to find in the iClear paper that he has. I don't know if you've seen this, but he has like 16 different or 12 different perturbations of images that are pretty naturally occurring kinds of things that can go wrong when taking a picture. And so if you could learn to recognize those and say, okay, in images that have these, it's just a bad image, so I should reject it for these reasons, which are really separate from how confident you are that it contains a duck or whatever it is you're looking for. So that's an interesting direction, I think. And as far as I know, no one has really looked at it. Okay, well, in the last 20 minutes or 15 minutes, let's look at this other technique called conformal prediction. So the conformal prediction framework is kind of related to rejection and kind of not. And it's a little bit tricky to wrap your head around the full thing. So the idea is we're given a set of training data, and I'm using these sort of double square brackets to indicate that it's a bag of instances. This is kind of important for the theory, but I think you can just imagine that it is a set. And so each instance ZI is actually a labeled supervised training example with the features X and a class label Y. And we're going to learn a classifier in the usual way. But in addition, we're going to have some kind of a nonconformity measure. And the nonconformity measure you can think of as something like an anomaly detector. And what it is a function that is a function of n-1 examples. We're in a fully online framework here, so we're going to be doing online learning. So these are our n-1 previous examples, and here's our new example. Or it maps from n-1 previous examples and a new example to a real value, and the bigger that value, the more non-conforming, the more distinct, the more unusual this new thing is compared to the n-1 previous things. And then we're given a query, and xn is our query point, and a desired accuracy level. So what we do is, and the goal is to output a subset of all the possible class labels. So a set C of your query. In this case, that should, I guess, be xn, but xq for query. A subset such that the true label yq is a member of that set with high probability. So that's what we want to achieve. Now, of course, again, we could always trivially achieve this by outputting the entire set of all k labels. So we want to make that set as small as possible. And in fact, from a rejection standpoint, unless that set of labels is a singleton set, we're going to reject the data point and say, we don't understand this. We can't confidently predict this. Now, the method that's used in the online case is a kind of leave one out strategy. So let's see if we can get this. So what we do is we say for each of the possible class labels, let's create a sort of virtual data point that consists of the query being labeled as being belonging to that class. And then we ask, how different would, if, I don't have this notation right. This should be znk, right? No, it shouldn't. Where does znk come in? Well, now I don't see where it comes in. In all these cases, okay, no, this is Zn, right. So this, I guess it should just have the K here. Right. Okay, so I'm missing a K superscript there. So we form a data set that consists of all of our previous examples plus this new fake example, but then we remove the ith example. And we get a score for how conforming this ith example is with respect to this training set. And we do that for each of the examples that we have. So we get, and we call those scores the alphas. These are the nonconformity scores. And this is for the case where we labeled this with class K. So we're going to let pk be the fraction of these things that are greater than or equal to the score that's assigned to our guy, which is znk, right? And so the intuition is if a lot of points have higher nonconformity scores than we do, then we're not so bad, right? And in particular, we would we're going to include in our answer the class K if this probability is greater than or equal to some value delta. So did I say that right? Alpha I is the degree of nonconformity. And so we're asking how many of the points in our data set got nonconformity scores that are bigger than us, so we're weirder than us. And if at least delta of them are weirder than us, then we think we're actually not so bad, and so it's okay to put, so class K is labeling us as class K would not be crazy, and so we should include class K in the answer set. Yeah, okay. Should I do that again? Or does it? there are simpler versions of it. So let's look at two simpler, well, first we'll look at examples of nonconformity measures. So one thing you could do is just use the minus log of the predicted probability, right, which would be the surprise. So the lower the probability f of zi is, the more nonconforming you would be. And one that they use in their experiments is nearest neighbor nonconformity. So they say, what is, if you have a training, sort of your training set B or your reference set B, and then you have this new data point Z, you can ask, well, what is the distance of Z to the nearest neighbor in B that belongs to the same class? And what is the distance to the nearest Z that belongs to any class that's different from the target class? And if that is big, then the same class is very far away compared to, you have a nearest neighbor that's much closer that belongs to a different class. So that's an example of a nonconformity measure. So in addition to outputting this set of possible class labels, we can output the one that gets the highest pk value, or which is the best prediction, or we can get what's called the p-value of the best prediction, which is the pq is the largest of those, and we can also get what's called the confidence, which looks at the how big is the probability assigned to the second highest class, and take 1 minus that. And so we'll have more confidence if the second highest class has very low p-value, very low value for pk. Okay, so the online case is a little bit elaborate, obviously. I always have a little trouble understanding it clearly. So one thing we can do is do more of a batch approach, right? And in the batch approach, we split our data into a training set and a calibration set. We train on the training set, and then we have these calibration points, and we calculate the nonconformity scores of each of the validation points in the same way, right? So again, we insert each of the validation points. Let's see, right? We just look at we do leave one out estimation of the nonconformities of each of the calibration points against the rest of the calibration points. And then given a query, we can calculate, again, for each class label, we provisionally label it as that class. We ask what is its nonconformity compared to the validation set. And then we say, well, what fraction of those values and this Q value are greater than or equal to this Q value. And if that's greater than delta, then we include class K in the answer. So the only difference here is that the value of ZQK doesn't have an opportunity to affect the other nonconformity scores because we don't include it in here. You remember before we included this provisionally labeled object as one of the objects in the data set. And we can go even further and view it just as setting a threshold. So if we just calculated our nonconformity scores for the validation set and let tau be the delta quantile of that set, then given a query, again, we could calculate the nonconformity scores for each of the different provisional labels of the query and include all the ones that had a nonconformity score that exceeded tau. So this has another difference, which is that the threshold is computed without considering the query. But if the sample size is large enough, then these two things don't really have any significant effect compared to the online ideal. So they did, there's one of the papers I cite, they did some experiments on 3 domains using a single hidden layer, so a 3-layer multi-layer perceptron with just one hidden layer. This is old style, so we just used a learning rate and momentum, and they used a couple of different nonconformity measures. And what they found was that, for instance, on the satellite data set, they set the confidence level to 3 different possible levels. And 60% of the time, when they set the confidence level to 99%, the conformal, the prediction set, the confidence set was a singleton. So we would not reject. And 39% of the time it had more than one label in it. And 0% of the time it had no labels at all. So you would consider it an error if the correct answer wasn't in the set C. And so we set the confidence level to 99%, and our error rate is 1.11. So pretty close to 1. It should have been 1%, right? And here it should be 5%, and here it should be 10%. And we can see as we relax the confidence level, more and more of the time we're getting a singleton set. So if we were rejecting, we would have had to reject 39% of the data points here, 16% here, and 3% here to achieve these target error rates. If you use the leave one out technique instead, you get basically the same results. It's slightly better on one case and slightly worse on another. And they did this for shuttle, and we're seeing in this case they never had more than one label. Sometimes they had no labels at all. So you would still have to do some rejecting here. So we would reject about 11% of the data and still get 11% error. Oh, well, this counts as an error. But from the classification point of view, we would be achieving very high performance doing that. So actually, shuttle is beautiful. And with segmentation, it's a bit more complicated, but we are hitting our target error rates, and most of the time, we're able to do that without rejecting anything. Okay, so then I thought, well, they weren't really thinking about it as a rejection mechanism, right? They're just thinking, you know, thinking about it more like a confidence interval. Instead of predicting a single class label, I'm going to predict a confidence set, and I give you this guarantee that with probability 1 minus epsilon or 1 minus delta, the right answer is in that set. And that's sort of a different question than the rejection question, right? Where I output one answer and I say with probability 1 minus delta, that is the right answer. So I decided to look at the batch simple thresholding version of this. So I trained a random forest on half of the UCI data set for the pen digits problem. And then I used the predicted class probability as the conformity score. So it's negative as the non-conformity score. I computed the tau values using the other half of the training set, and then I computed the set C on the test set. And here is my empirical distribution for the class 9 in terms of how confident I am, and this is the score assigned to class 9. And so here are the results. It turned out that the selected tau values were all 0. I originally started, I think, with epsilon of 0.01, but it turned out that it chose 0, and that achieves an epsilon of 0.001. So let's say I was looking for an epsilon of 0.001. Then it turns out the probability that y belongs to, gamma of x, that's the same as c of x, is 0.9997. Okay, so it certainly achieves 0.0003, but it has to abstain 72% of the time. So not very good. And these are the sizes of the confidence sets. So I only get a singleton confidence set 28% of the time, which is why 72% is the other answer. And sometimes it even outputs, very rarely, all 10 class labels. So that was kind of discouraging. So instead, if I just thresholded on the estimated probabilities, p hat, then this is what the curve looks like as I set the threshold. I can get my number of validation errors, to go very low. And if I zoom in the region around making just 1 or 2 errors, I end up with, if I set delta equal to 0.05, then I don't remember how many errors that turns into, 0.87. So it must be 2 errors. I can hit this value here. So I use tau equal to 0.87. And with that setting of tau, I hit an accuracy, right, of 0.9987. And with rejecting 33% of the points. So it seems like simple thresholding is much better than conformal prediction. Because in some sense, when conformal prediction, in simple rejection, I just reject it. Whereas in conformal prediction, I don't get to reject it. I have to also say, well, it's not this class label, but I know it's either this one or this other one. So it has to tell you more. Conformal prediction has a harder problem. not only saying, well, this is the most likely, but I'm going to give you a small set of labels, and I guarantee it's one of them, which is a stronger statement. I mean, especially if you imagine you had 1,000 classes, like an ImageNet, you'd want to give, we would look at something like, I mean, very often they report top 5 accuracy in ImageNet, right? So that's thinking, well, if I'm going to output a set of size 5, what would those 5 be? But there is another use case, I think, for conformal prediction that I've seen in just a couple of application settings. And so while it seems like conformal prediction isn't very useful for rejection, I think it is actually perfect for this. So there's a group at the University of Buffalo, SUNY Buffalo, right? They are kind of the leaders in document analysis and handwriting recognition. They've done a lot of application work for the US Postal Service. And in fact, the handwritten zip codes on envelopes are all read by their system in the United States. So it's a big successful application. They didn't use deep learning, but they had 2 different classifiers that they built. One was very fast, but not always accurate, and the other was slower, but much more accurate. And these envelopes are coming in a robotic apparatus. They're coming at a certain rate, and they scan them, and then they can hold them in a little buffer for a little while. And if the first classifier is not confident enough, they're going to have to buffer them longer before they can release them they're sorting them into bins. And so it turns out they can only afford to buffer 1/3 of the envelopes. For the time it would take to run the slower classifier, right? So basically with the faster classifier, 2/3 of the time they have to get an answer out of the faster classifier and go with it. I mean, on average. To avoid this buffer overrun problem. And then 1 out of every 3 envelopes they can afford to take longer. So they don't call it conformal prediction, they talk about what they call vocabulary reduction. Because one of the things you can do with method 2 is if you give it, if you say, I don't know whether it could be any of the 10 digits. It takes longer than if you say, well, I think it's either this digit or this digit. So it has a sort of separate model for each digit that it's using. And so if you can reduce the set of possible answers that it has to score, it runs faster. So the idea here is to do what they call vocabulary elimination, which is, can I rule out some of the class labels with the fast classifier and then call the slower one, and it takes longer, but the more I can reduce the vocabulary, the faster it can go. And if it's reading letters, then, so there's something, I can't remember how many symbols they handle, right? There's the number sign symbol, probably the ampersand, all the letters of the alphabet, upper and lower case, periods, and stuff. So they have to read the entire handwritten address. So you could use the conformal prediction using on the classifier from method 1, and then apply method 2 if your class is greater than 1. But you would have presumably reduced. Hopefully, C of X is not all the possible labels, but some much smaller set. So maybe there are use cases like that. Other people looked at cascades of classifiers that are progressively more and more stringent, but maybe also more and more expensive. So I think there are lots of applications like this. Okay, so in summary, in lecture 1 we talked about calibration. In this lecture we talked about rejection. And so we first looked at thresholding, we're learning a function and then thresholding it at single or multiple thresholds. If you use multiple thresholds, then you end up with that double hinge loss kind of approach if you're using the SVM methodology. In method 2, we think about learning a separate rejection function and then thresholding it. And we end up with that interesting 2-dimensional loss function and the complexities that it introduces. And then in method 3, we could use conformal prediction, but this violates Vapnik's rule that we are solving a more difficult problem on the way to making our rejection decision. But it still might be useful for doing this lexicon reduction or vocabulary reduction. So as I say here, in my experience, conformal prediction is not very good for rejection, but it's only based on that one experiment. Well, and a few other things we've done along the way here in the past few years. All right, so if we get around to my third lecture, It will be about open set classification, and really we should have Rishik and Sue give it because it's mostly about their work. But I'll see you next time, I guess. Questions?
I had one question about this last one. We talked about the second classifier in the postal
Right.
section. Is it kind of tuned to the set of classes it is looking at, or is it
Right.
the same classifier?
Right, so I don't remember the details of how it works, but it only scores the classes that you give it. And somehow the compute time that it takes is proportional to the number of things it's scoring. I may be confusing it with another one, but they had, I believe that the first classifier actually, in their thing, looks at whole words. It sort of looks at the shape of whole words. And the second one uses an HMM type of model, and so if you can reduce the set of classes, that whole the structure gets smaller. Yeah, yeah. The trellis, yes, is much smaller if you reduce the vocabulary. Yeah. But I don't know, nowadays we just put it on a GPU and maybe no. But the thing is, of course, you could probably speed up the hardware then if you can make the classifier faster, right? It's a good example of hardware-software co-design.
Yeah, the data set was used a lot in the deep learning methods to kind of...
Well, there's the MNIST data set, but I think this is a bigger data set that involves, because the whole system they built has to find the address block on the envelope, right? And then try to parse it into its various pieces and then recognize each one. And they have, the Postal Service has a claim to be complete list of all possible legal addresses in the United States, right? I don't know if you ever go to the U.S. Postal Service site to temporarily stop mail while you're going to be away. It checks against that and says, no, there is no such address. And you say, yes, there is. I get mail at it every day. Yeah, but another, if you're looking for, I think, a whole thesis project is, so now we're very interested, right, in transfer learning and meta learning and things like that. So just as I mentioned last time in calibration, what if you trained a classifier and calibrated in one domain, but now either there's been concept drift or there's been, or we're transferring to a new domain? We're all excited these days about few-shot learning and things like that. How could you do few-shot learning and still give calibrated answers or a good rejection function? It seems like there's a risk. The standard way of doing transfer learning, right, is to learn basically a latent space in which the two domains look the same. But I would think that if you had a rejection function you learned in domain 1, it would be rejecting the things in domain 1 that really don't look like they're from this shared space, right? And in domain 2, domain 2 would be different in a different way, right? Presumably from this shared space. So I don't know how you do it, but I think it would be a very interesting thesis topic. So we should cut that from the web version.
I have one more question about the DHL and the CHR.
Right.
So what's the source of the, superior performance of CHR? Is that a loss function design, or is it?
I think it could be that, that with the separate reject function, they can handle this problem in a way, I think. I haven't thought about this. I mean, they have this extra degree of freedom that the decision boundary of the reject function can be very different from the decision boundary of the classification function. So I suppose in this case, they could learn to reject all these points because they're getting them wrong anyway. Yeah. But I don't know. Yeah, I'm just an outsider reading this. But it seems like they do have this extra degree of freedom here to learn two functions instead of one. Yeah.
For the KV classification setting you told there aren't any methods, right? Is there any particular reason, like if we do a Bayesian version of it, like single threshold might be sufficient for all classes?
Well, I don't know. I haven't thought about it very carefully, but
I get anomalous.
I mean, you would be taking the argmax of all your classes, right? This is what we do nowadays.
I'm saying if I could get the true Bayesian posterior, what is the predictive probability of all the other classes, and then I get the true Bayesian posterior of the current class.
Okay, and then you would use a cost matrix of some kind.
Yes,
to
and then
decide.
if I use that
Right.
to get a threshold, are there any potential downfalls with that?
Would it be a threshold? I mean, your posterior is going to be k-dimensional distribution of some kind.
Summit.
Yeah. I mean, I just haven't looked at it, but I don't know of anything in the literature that says that having a single threshold or a separate. I mean, if all the errors are the same, cost the same amount, then I think a single threshold suffices. But the interesting case is when you have an arbitrary cost matrix, and now you want to make minimum cost decisions. And it seems like now in a K-class situation, you're somehow trying to integrate the costs over all of those. And so it's really just a question of that you have a K-dimensional integral to solve.
Yes, I mean, in that sense, I can integrate with cost as well. I can just multiply the cost with respect to the.
But then you have your posterior.
Yes.
Yeah. I mean, so yes, I think you can write that down, but and so maybe the challenge is to get an efficient algorithm for it. Yeah. Okay, well, thank you very much. Enjoy.